Okay, we're going to begin. Do we have homework today?
No.
No. We do? Cylindrical coordinates, we started that. I did a couple examples, but I wanted to do more.
You did only one example. No homework? No homework?
Let's do some more examples here.
Yeah.
How about that one? How do we set it up? What is the object Q? Huh?
Cylinder?
Cylinder? What kind of cylinder?
Up, going up. Is the axis. And
It's a circular cylinder. What's the radius?
the
There's a circle here. It's going through 3. What else do we know about it?
the plane Z is equal to pi.
Divided by Z equals 5.
Okay. What does Z equals 5 look like?
And not a circle.
Well, it's a plane parallel to the XY plane, right? So here I'm actually giving you a finite cylinder. Q is just a finite circular cylinder. The height is? That's 5. Right? So this is me describing an object to you, which is a cylinder of height 5. Okay. Now that you know that, how do we actually evaluate this integral?
The first integral is from 0 to 2 pi. First, let's change everything to cylindrical coordinates. 2 pi is equal to 3.
Why would you think cylindrical coordinates? Besides the fact that we're at 12.6.
Circle.
Because the intersection here, the region of projection, is a circle, right? So you're going to look at that as D.
And there's symmetry, that's important too.
Symmetry where?
Symmetry in the balance of the circle is symmetrical.
Symmetry is less important. What's more important is the circle. Okay, so how do we set up that circle?
R is 0 to 3.
R is 0 to 3. So circle radius 3. It's the entire cylinder. Theta is 0 to 2 pi. Okay, so that gives you the 2 outer integrals. Remember, your region of projection give you the 2 outer integrals. The inner integral is Z, which is what? 0 to 5. 0 is the xy plane, 5 is that, right? Top surface, bottom surface. Okay, so this means the triple integral of e to the x squared plus y squared, which we can integrate with respect to x or y, by the way, is equal to integral from 0 to 2 pi, 0 to 3, 0 to 5,
To the R.
e to the r squared times
R D D.
r
DR.
dz dr dθ. So there's no theta in what I'm doing here, so
Two.
There's also no z.
there's also no z, so how's that going to change things?
You just make it 10 pi on the outside.
Right, there's going to be a 2 pi from the theta.
Yeah.
From the z, there's going to be a 5, right? And we're left with this guy. What's the derivative of that? The integral.
1/2 e to the r squared.
So you plug in, this cancels out to 5, so you get 5 pi e to the 9 minus
5 pi.
5 pi. Not so bad. Okay, how about this example? Ideas?
Where you change everything you want.
Draw it first.
What?
You draw the area, the region of projection from the first two integrals, and you can see what it is and change it to total. Or
Right, so sort of doing this dz, dy, dx is not really something I'd want to do. I would have to be integrating using something like a trig substitution. It's going to be horrible, we can see that. So one thing you want to do is you might think of change of coordinate system. Hopefully you start to recognize these guys and we can start to draw them. How do we figure out to draw them? Right? So here we're given an integral, we want to go back to a surface like this. How would you,
I change it in terms of r.
where do we start?
As a beginning, so like the bottom one
Is that? Yeah, tell me.
Since you know the, I guess the z bound, you could draw that out, just to like get an idea of the figure.
So you start with the inner integral? Okay, so if you're drawing the z bounds, what are we doing? Notice that the z bounds are the guys from this integral here. So that we're talking about, we're going from z equals x squared plus y squared up to z equals 2 minus x squared plus y squared. What does z equals x squared plus y squared look like?
Parabola.
Paraboloid opening up.
And the second is a paraboloid going up, opening down at the value 2.
So maximum point is at 2, it's opening down. Right? So our object seems to, the intersection of those guys seems to be this. Okay, so that's sort of what in the 3 dimensions we're dealing with. What about in 2 dimensions? We're talking about the region of projection.
that's going to be the xy plane.
Right, because those are the 2 guys on the outside, so those guys tell me what plane my region of projection is. Notice that my x values go between -1 and 1. My y values will go between this guy, right? So I know my x is going between -1 and 1. What does y equals the radical of 1 minus x squared look
It's
like?
the top half of the circle.
It's a semicircle. And its radius is actually 1. So that would just be like this. That's my top curve. This would just be the bottom half, bottom curve. This is my region of projection. Right? Which If you intersect this with that, you'll notice that this object falls exactly on that region of projection. It might not have, by the way.
But if it did, doesn't that mean that the integral was originally set up wrong?
No, it could mean what I want is just the volume under a smaller region of this object,
Okay.
right? So I could do that.
But it couldn't be bigger, right? Also do what we would.
Well, yeah, but we'd have to worry about parts out here and things like that. Yeah, there would be other considerations, but this one happens to overlap exactly onto that, right? I can set these two equal to each other, and the intersection would be x squared plus y squared equals 1. So we're fine in any case. But it's something that you do have to check. You have to check the objects here and here separately because they might not overlap in the way you're expecting. Okay, so now that we have that set up, how do we set up the integral? Describe this. Okay. And my z? Huh?
R squared.
R squared up to 2 minus r squared. So it means that this integral I could set up as 0 to 2 pi, 0 to 1, r squared up to 2 minus r squared. This guy, x squared plus y squared is?
R squared.
R squared to the 3 halves, the 2's would cancel, I just get r cubed times r dz dt. Okay, how do we do this? Well, I know the thetas are going to give me a 2 pi because there's no theta involved anyway. So I can just take those out. Why can't I do what I did with the z last time and just take that out? Right, because my z includes r values. It will actually change the function, so I can't do that. I have to just slow down and actually evaluate everything. So 0 to 1, this is going to be r to the 4th times z, integrating with respect to z. This goes from r squared up to 2 minus r squared dr. So it's r to the 4th times 2 minus r squared minus r to the 6. R to the 4th minus r to the 6, which means 2 r to the 6. Integrate that, we get 2/5 r to the 5th minus 2/7 r to the 7. We could have taken a 2 out, sure. So this is 4 pi times 1/5 minus 2/7.
Minus
You took out the 2, so it's 1/7.
1/7. Which is going to be what? 4 pi times
8 pi over 35. So it's 2 over 35.
Okay. So do we have this? Do we get it? What if I put a 0 here?
We're only do the top half.
It's theta from 0 to pi.
So it'd just be like literally half. of
What
it,
would have
so
changed?
The region of
The
projection.
theta would have changed, right? I would have went 0 to pi. Okay. All right. What if I had put a 0 here?
It would have been from negative pi to pi. Sorry, negative pi over 2 to pi over 2.
Again, I'd only affect the theta, yes, from negative pi over 2 to pi over 2.
It'll be.
So it would be pi over 2 to 3 pi over 2.
Just checking. Here's another problem. Find the volume. The solid bounded by that's my last example. Find the volume. Right, that's what you start by doing. Okay, what does this look like? Well, they told me it's a sphere, so I know what one of them looks like. Sphere, radius 1, centered at the origin. And what's the other guy? What's this guy?
Cone.
Top part of a cone, opening where? Up to the Z. What's the region bounded by both these surfaces?
X squared plus y squared
Two
equals 1,
circles.
right?
It's like a wedge.
It's a two
Come again? The region bounded by, not the region projection, the 3D area bounded by.
It's like the wedge.
So it looks like the ice cream cone. So it's this guy here, an ice cream cone. Okay, so that's the object. I want you to find the volume of this wedge, or well, it's not really a wedge. Okay, so what do we do?
You have to find the region
Find
of
it,
projection.
intersection.
Okay, how are we going to do that?
Find where they intersect to get the.
Well, you have to
Right,
find-
figure out where the surface and this cone intersects, and we're going to project that down. Seems to be the natural thing to do here. So let's try to set that up. It seems like the region is going to be a circle, but exactly what circle where you sort of find the intersection. So
So that is even more.
what's that going to be?
1, right to x squared plus y squared
X squared plus y squared plus what?
equals 1. Wouldn't it be where z is 0?
No.
It's where the z's equal each other.
It's where the z's equal each other.
So you have z is equal to r, and
1 minus
r squared plus z squared is equal to 1. Then you have r squared plus r squared is equal to 1. Then r is equal to 1/4.
Yeah. Or you can literally just substitute this one here. If you plug in radical of x squared plus y squared into here, you square it, you just get x squared plus y squared. So you actually have 2 x squared plus y squared. Let me write it out. So you have x squared plus y squared plus the radical of x squared plus y squared squared. So you have 2 x squared plus y squared equals 1. So we have x squared plus y squared equals a half. So what's that?
R is equal to the square root of
Right, so it's a circle of radius 1 over radical 2. So this means I can tell you my bounds for r, I can tell you my bounds for theta. I can tell you my bounds for z. R goes between 1 over radical 2 theta. Z. Right, so you solve for z here, which is the top surface. So I would get the radical of 1 minus x squared minus y squared, which is r squared. Technically solve for z, you get plus or minus, but we don't care about the minus part. The minus part will give you the bottom part of the cone. So we ignore that, we just take the positive radical, and those are our limits, which means our volume is equal to what? 1 sine phi. How do we find volume? In general.
1.
Huh?
Triple
The
integral
triple integral
over d.
of 1 dv. That's how you find volume, over whatever the object is. Here we can describe the object in cylindrical coordinates, so I'm going to do that. 0 to 2 pi 0 to 1 over radical 2, r up to the radical of 1 minus r squared. This becomes r dz dr d theta. And that integral will actually give me the volume. Evaluate. Sure, we can throw out that 2 pi. Right, the integral here would be r times z. I plug in z equals this minus z equals that. So I would have 0 to 1 over radical 2 of r times the radical of 1 minus r squared minus r squared. And what's that? What's the integral of this? What do you mean 1 minus r squared? You mean 1 minus r squared to the 3 over 2?
Yeah.
Times 2/3.
Yeah.
And then
So you need negative 1/2.
we need negative 1/2. That would come from the substitution. Right? So this actually gives you negative 1/3. And you can even check it. If I were to differentiate that, I'd bring this down. The 3's would cancel. I'd get a half. Multiplied by minus 2r will kill the negative and the other 2 here. So that's actually my integral here, minus the integral of this, r cubed over 3. I can take out the negative 1/3, sure. So I have minus 2. What happens here? 1 minus 1/2, which is just a half, minus, plug in here,
There's also same thing.
1/2 to the 3 over 2. Oh, wait, I took out the thirds. I took out minus a third, right? So that's a plus.
What if you 1 over 2 radical 2? But it's 3 exponents. It's r.
1 over 2 radical 2. That is 1 over 2 radical 2. That's the same thing. Because I put 3 over 2.
Oh, okay, I see. Yeah.
So minus, when I plug in 0, what do I get?
1.
Just 1, and then that's gone. So this is minus 2/3 pi. Yes, this is 1 over 2 radical 2, but I have 2 of those, so it's just 1 over radical 2. And that actually makes sense because that's the same as that, and 1 is bigger than 1 over radical 2. So this is actually a positive number. Okay.
Well, you can just add those fractions and exponents up like that. And you just make the both things 1 over radical 2.
Well, I just add these, so I get 2 times 1 over 2 to the 3 over 2. Which is 2 times 1 over 2 radical 2. And the 2's cancel. What if I had said I want the volume of the solid bounded by those 2 surfaces in the first octant?
The theta would have changed. It would have been 0 pi over 2.
Right, I would have changed the theta. What if I had said I wanted to bound z squared equals x squared plus y squared and this sphere? How would that change?
It'd be 2 times that. It would be on the bottom also.
Right, it would double that, right? Because you just have this sphere and then there's the cone going through it, and I want the volume of all this. Okay. So, should know how to go from the words and the formulas to the shapes and figure out how to get to those. It seems like some of you have gotten it. So, how's integration so far?
Oh, it is.
Yeah?
In the homework for this section, it had some where it was doing like the center of mass of like a solid.
Okay.
Is that something we're gonna have to do as well?
Yeah.
And it's basically the same.
It's
as
basically
other
the
one?
same. You have the formulas. You just apply the formulas. So it's just going to be like the x bar is 1 over m times the triple integral of x times rho dv. Right? So basically the same formula is generalized.
Okay.
You're just doing triple integrals now over and over. So we're okay with integration so far, right? Is it hard? Is it the hardest chapter we've done so far, or is it?
Yeah.
It is. It's the most difficult.
Because you have to rely on older stuff that you've probably forgotten, so.
Those double angle formulas kill me.
Yeah. I don't want to say that in my life.
I don't
It's not
know.
hard power, it's like a double angle formula, like.
You guys seem to respond faster when I ask questions, though. I don't know if that's the topic or maybe it's because finally worked you guys into shape with all those quizzes. You guys are always on edge. Can't answer any math question at any time. Oh my god, Joe's gonna jump out from behind me and ask me something. Okay.
Walking fast is not out of place.
It's funny because every now and then I catch students and I actually do that. Like I'll see them like getting coffee and I jump behind them. Ask them a math question. What's the like a form for sine? I'm just having my coffee. So. Yeah, like if I catch you, I'll ask you a math question. So yeah, you guys are answering too fast. I think that means what we're doing is too easy. So let's do another challenge. Spherical coordinates. A different coordinate system altogether. So we did cylindrical coordinates and we really liked using that whole angle thing. So we decided, hey, let's throw in another angle. And you get spherical coordinates. As the name suggests, this is sort of useful when you're integrating over regions that are parts of spheres, right? So like cylindrical coordinates, you sort of look for the region of projection to be circular or part of a circle or circular-ish, right? In spherical coordinates, now you're looking at a 3D object, and once you can see, oh, it's a part of a sphere, spherical coordinates might be the guide to use, because it's really sort of looking at the 3D world in terms of spheres instead of rectangles. So cylindrical coordinates looks at the 3D world as a bunch of cylinders instead of rectangles, right? So that's really where the difference is. I started out with a diagram, so let's actually do that. Locate a point in what we call spherical coordinates. Okay. So spherical coordinates is partially polar, right? So let's say there's a random point here in three-dimensional space. I want to locate that point. Here's how we would do it in spherical coordinates. Right? Just like in polar, we're going to use the angle theta in the xy plane, the same old theta from polar coordinates, right? We're going to swing around so that we're right below that point, right? But the thing is, we're not going to just jump from here. That's sort of not looking from an angle. Right? So just like before in cylindrical, we use this theta to swing around to get right below that point. The thing is though, we're not just going to jump up to that point. What we are going to do is we're going to think of this point as lying on the surface of some sphere centered at the origin. Right? So what we're going to do is we're going to realize that the distance from the origin to that point, we're going to call it something. We're going to call it rho. Right? So we're looking at another radius, right? So it's not the radius in the xy plane, which is still r, by the way. It's just the same theta from polar coordinates. Now we look at another way to do it. assume that this point lies on a sphere centered at the origin of radius rho. And what we do is we figure out another angle to hit that point that is measured from the positive z-axis coming down. This angle we call phi. So now we have two angles. There's one angle that swings around just below the point. There's one angle that swings down to hit that point. And then there's a length from the origin hitting that point, which is thought of as the radius of some sphere. Yes?
Isn't that pronounced phi?
Tomato, tomato. I pronounce it phi because there's another letter called psi, and then you just kind of mix that up. Right? There's a psi and then there's a phi, so I just try to. Anyway, so these are what we call them. That reminds me, there's something I need to remind you pretty soon. Okay, so theta, just like in polar coordinates. Rho is the distance from the origin. Right? The really new guy is sort of phi, which is this angle. It's measured from the positive z-axis. Let me write that where I can write it. Phi is an angle measured from the positive z-axis downward. It will always be within the range of zero to pi. It will always be somewhere in between those two values, or a range somewhere between those two values. Okay. So let's sort of see how this would work. Now, some remarks. Theta lives in the xy plane. However, phi does not live in any particular plane.
Is it either the z-axis or y, right?
Well, I'm going to talk about what everything is setting up. So I just want to sort of describe our new concept of the world, right? So basically, the idea is if you think of 3D space as just a bunch of spheres all centered at the origin, right? Just a bunch of, you look at it as like all spheres. And at any given time, any point in space can be thought of as sitting on the surface of a sphere. What can happen is, no matter where your point is located, you can always swing around with a theta, and then you can open an angle all the way down as far as you want. You will never actually have to go beyond the angle pi, right? So you might say, well, what if I want to go past angle pi to hit a point around here? Well, that just means you just needed to swing your theta around to the back, right? Phi depends on theta to get it to whatever region it needs. It will just open from the positive z-axis all the way down to the negative z-axis, and it will hit all points in that range. If you want to go to the back, you just swing your theta around to the back. Right? That's sort of how you can do it. So it will never actually have to actually exceed an angle of pi. Right? You can hit any point by doing that. Right? Any point behind here, I just swing my theta around there, and then open this way, hit that with a distance rho. Right? I'll always be able to hit any point, and I will never have to go beyond the angle pi. So that's one new concept. So phi doesn't really live in any plane. You just depend on the theta. You swing it around as far as you need with the theta. And then the phi will be somewhere between 0 and pi to hit this object.
So they're kind of creating their own plane together?
Together they're creating their own plane. So there's this plane that you can sort of create. Let me continue over here. So here's the point. Remember that's line. This here is your R, that's your rho. This is your phi. This is your theta. Right? Notice that together, these guys, these lines here will span a plane, right? You can think of this as a right triangle. Right? We can think of those as a right triangle, and this is like a plane that they span. And this plane can be rotated anywhere around this guy here, and we don't need, that's pretty much everything. We can just rotate this plane. So the phi doesn't live in any plane, but the theta is always in the xy plane.
And that's how by using the R and the Z we could find what rho is?
Yeah, so now we're going to have to figure out the equations that govern this kind of conceptualization of 3D space, right? So we know, like, if we're thinking in polar coordinates, we know things like x squared plus y squared equals r squared, or x equals r cosine theta, or y equals r sine theta. What are the equations that governs this kind of coordinate system? Well, yeah, we're going to basically use trig to figure it out. So for example, you might have remembered from high school geometry that that angle will also be phi. Right? Of course. Yeah. You're totally right. Yeah. Okay, so if we're in a right triangle, this is rho, that's phi, this is r, this is phi. How could I describe, say, rho or phi or one of these guys? Like, for example, how would I describe the z coordinate? Z would be the height here.
Square root of d squared minus
Okay, so cosine of phi would be adjacent over, right? So if I take cosine of phi, I would get adjacent over hypotenuse. Therefore, I can think of my z coordinate as being given by the equation rho cosine phi. Right? What about my x and y coordinate? How would I figure out my x and y coordinate?
Sine phi. Then R.
How is that x?
Come again? So I know that x, for example, in polar coordinates is what? R cosine theta, right? Try to get a phi in there. How would I can I express a phi, get a phi to be applied here?
Isn't that like sine phi is equal to R over rho?
Also, if I take the sine of phi, right, what would I get? Opposite over hypotenuse, that's r over rho, which means that I can actually write my r as rho sine phi, which means my x would end up being, this r I can replace with rho sine phi, cosine theta. That's my x. Similarly, y equals r sine theta, which means it's equal to rho sine phi sine theta. Putting these together, you'll notice something very curious. If I take x squared plus y squared plus z squared, what do you think I'm going to get?
Rho squared.
I would end up getting rho squared. You can do this for yourself. It's just applying the Pythagorean identity. You're going to apply that sine squared plus cosine squared gives you 1. And you'd end up that. These end up being the equations that will govern this coordinate system. So if you think of the world in this way, here are the equations that will describe this world.
Wait a second, for y, you said phi equals sine phi sine phi or sine phi sine theta?
That should be sine phi sine theta. I'm just replacing the r with rho sine phi. Hence we obtain these equations. So for spherical coordinates, x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi, and x squared plus y squared plus z squared gives us rho squared. Now for this I have no explanation, but it's something that you should note for the engineers. In your engineering classes, theta and phi are switched. I have no idea why they decided to switch it, but they decided to switch it for some reason. So if you're reading an engineering textbook, think of the phi as the guy from polar coordinates, and this is the new guy that you just thought of.
Wow, that's good. That's good.
I have no idea why they do it, but it causes people a lot of confusion. So you spend your whole life thinking of theta in one way, and then you get to engineering like, no, we're going to call it phi now.
Also, whereas the coordinate axis.
Yeah, they might orient it differently. So they might also, yeah, I should mention that. I don't remember the exact orientation. They may also orient the axes differently. So yeah, so you need to really get this to the point where you can switch variables around and it shouldn't bother you, right? Because they are going to switch the variables around on you eventually. Just a word of caution. Okay, what else do we want to say? Okay, the volume unit, dV. dV also ends up being kind of weird here. Let's look at the volume differential unit. Right, that dV guy, what would he look like? Right, is the question. So here, again, the volume unit would look like this. There'd be this guy on the inner surface of a sphere, that guy on the outer surface of a sphere. I want to show the bottom of this. Yeah, so there's going to be like a row 1 to hit this guy, and a row 2 to hit the outer one. Row 1 to hit here, row 2 would hit all the way here. There's going to be a change in phi. right? This is going to be like your delta phi. There's also, if you project this in the xy plane, there's going to be a delta theta here. That's going to be that change in the angle. Basically, if you look up the volume of this, you sort of pretend it's small enough to be thought of as a rectangle, sort of do a length times width idea. Think of this as a infinitesimal rectangle. Then we assume. Basically, the idea is if you zoom in far enough, these curves sort of look like straight lines, so you sort of pretend they're a rectangle. And then you can take a limit. We assume volume of this guy equals length times width times height, which is going to end up being delta rho times rho sine phi delta theta times rho delta phi. That should be fair. So this means that your dV that's your new volume unit. Rho squared sine phi. So basically, now I'm going to tell you the punchline. Yeah, because this is all just a bad joke. And I'm going to need a lot of space for this. You can, I mean, this is just for edification purposes. You can work this out. You'll never have to derive this. It's just something that you should just know from now on. Just as how you know in cylindrical coordinates dV is just r dz dr d theta. In spherical coordinates, your dV is rho squared sine phi d rho d phi d theta. It's just something we know now. And what's going to happen is, if we're given a triple integral over some object of f of x, y, z, dv, basically this guy can be translated into a triple integral where your x will be replaced by rho sine phi cosine theta. Your y would be replaced by rho sine phi sine theta. Your z would be replaced by rho cosine phi. And then your dV becomes rho squared sine phi d rho d phi. This is theta 1 to theta 2, d1 to d2, and rho 1 to rho 2. So rho may be a function of theta and phi. Phi may be a function of theta. Theta would have to be constants, right? If you're setting it up this way. So this guy is a function of theta and phi. It could be, well, you always do want to think of it that way even though they don't show up. This guy is a function of theta. Because you can see he also sort of depends on theta a little bit. For him to reach around somewhere, the theta is what's going to get him there. And this guy will end up being constants. And he's the guy that's familiar, just like polar coordinates, the same idea that you had in polar coordinates works here. sort of how the rho is kind of like the r, but again, it doesn't lie in a particular plane. It lies in whatever plane that these two guys span. So this guy depends on those guys, therefore it's a function of them. And that's basically the idea. And again, why would we need such a coordinate system? Well, there are certain cases where it makes your life easier. I know it's hard to believe right now, but tripolar and cylindrical coordinates felt that way the first time we saw them. Like, why would we even do this? But as you can see, there are some integrals that were impossible for us to do before, but with cylindrical coordinates it was possible. Same thing with spherical coordinates. It can actually simplify our lives a lot. Especially now, we can't just get out an x squared plus y squared. We can throw in a z squared if we want to, and turn an entire sum of 3 squares into 1 square, right? So that is a very powerful technique. Let's actually look at some examples. Did I actually describe any objects here? Okay, let's look at some surfaces first. I sort of did a couple of these with cylindrical. Let's look at some spherical ways of representing a surface. Let's say I gave you a sphere. X squared plus y squared plus z squared equals c squared. Right? This is in rectangular coordinates, that's the equation. What would it look like in spherical coordinates? What's the equation of that sphere?
It would be p sine e cosine theta squared.
Well, it's rho.
Oh yeah, that's fine.
It's not a p. This is rho to Greek letter. It's actually the same variable we used for density before. Yeah, again, you're thinking too hard. X squared plus y squared plus z squared is rho squared. So this just means rho squared equals c squared. Rho is a distance, so it's always positive. So essentially, this just becomes rho equals c. Right? So the equation of a sphere is rho equals a constant, right? Where the constant is the radius of the sphere. So if I can say rho equals 3, that's me saying, oh, there's a sphere of radius 3 centered at the origin. It's exactly the same as me saying that. Right? So a sphere can just be described as rho equals a constant, right? This is the set of all points where the distance from the origin is c, because that's what rho is, the distance from the origin. I never planned on doing this, but what would this look like in cylindrical? It would look like r squared plus z squared equals c squared, in which case your r could be thought of as like the radical of c squared minus z squared. So you'll notice that in terms of if this is actually a sphere, spherical coordinates actually gives me the easiest representation of a sphere. It's a stupid little equation with a constant. What about something like, how about a plane? What about the plane, say x equals y, for example?
You know that in spherical coordinates?
Rho sine
Cosine theta is equal to sine theta.
Cosine theta is equal to sine theta, which means?
Theta is equal to theta.
Well, you give me an angle,
Oh, it's 45.
so pi over 4, right? So me describing a plane, and planes will always look sort of like this. So a plane can either be theta equals something in spherical. By the way, in cylindrical, it would actually be the same thing.
Can you explain why you did that?
Huh?
I know that theta equals pi.
Because we're in the xy plane, x equals y looks like this. The angle here is pi over 4. which is theta.
Now, if that was z equals y, then it would be phi pi over 4, right?
If I was in the plane z equals y,
Yeah, and wouldn't that be phi over 4, or phi pi over 4?
well, you'd have this guy's rho cosine phi, right? This guy is rho sine phi sine theta, right? So this would cancel here. And so that would sort of be the equation. There would be a relationship between these guys. So this would be something like,
Cotangent phi is equal to sine theta.
cotangent phi equals sine theta. Yeah. So depending on which one you want to solve for, usually since the theta is going to be the guy on the outside, you could actually solve for the theta. So theta is going to be sine inverse of cotangent phi, which you could simplify that if you want into other coordinates. Yeah.
But this follows the same principle where, you know, in cylindrical coordinates, how you could look at it in different perspectives. You could look at it, like remember when you did the type 1, 2, and 3?
Yeah.
We can't do this here?
We usually don't.
There's no need to.
There's no need to, exactly.
Sphere, okay.
Like, it's always a sphere. Like, you can hit any point with a sphere.
Okay.
What else did I want to describe? How would a cone look? What about a cone? Something like z equals the radical of x squared plus y squared. Coming up? Yeah, z equals to r. Can I use that to get an answer for the here? Phi equals pi over 4 would be the answer. Right? So here I have an equation that's a constant. Here I have an equation that's still a variable that I have to deal with. Right? So cones are usually just phi equals a constant. It actually describes a cone in spherical coordinates. Right? So you'll notice that there are cases, the equations here, they can look ugly. Equations here can sometimes look ugly. If it depends on theta, the theta is the same, so it's not going to make a difference. But look at the spherical coordinates for all of these. Very simple, very short equations. They all happen to be constants. These are all the kinds of surfaces that we deal with all the time. Spheres, planes, cones. They're really very short equations when you think of things in terms of the spherical coordinate system. Right? So that's just sort of giving you an idea of why we'd want to do this. Let's actually do some examples. So make sure, so for spherical coordinates, the important things to know are this, right? The equations for spherical coordinates: x equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi, and x squared plus y squared plus z squared equals rho squared. And how to translate these, you just plug those guys in for x, y, and z. Your dv becomes rho squared sine phi d rho d phi d theta. Let me add that equation here. So it's in a box, so you know you have to remember it. In spherical coordinates, as we were just mentioned, there's also never really a need to change your perspective. You'll never really need to, oh, let's look at the world this way. Like, you don't need it, right? The sphere already encapsulates all views. The sphere is like fully circular, going all the way around. Like, there's usually no reason to change anything. So this you need to know. All these equations are important. How to translate are important. And of course, using those equations, you can figure out the equations of surfaces that you deal with all the time, like spheres and planes and cones. So we have that. Let's actually do some examples. here's a nice integral. Triple integral over e of cosine x squared plus y squared plus z squared to the 3 over 2. dv. Where e is wouldn't even waste our time representing that in rectangular because we can't integrate something like that in rectangular coordinates. Again, if I switch to polar coordinates, what would I have to deal with? Cosine of r squared plus z squared. I'd have an r dz dr d theta. I could still sort of get away with a substitution, but it would be a lot nicer if this were a single variable. That's what I think. Yeah, that's what I think. Okay, so now the unit ball is just the sphere centered at the origin. Radius 1 is the solid ball. Okay, so that's our object. How would we describe this in spherical? Right, so theta is 0 to 2 pi. Okay, so that we know. Okay, because theta is just the same old guy that we had from polar coordinates. Okay. What else? Phi would, or phi, be 0 to pi, right? So theta swings me all the way around, and pi covers everything from here all the way down to here. So I'm getting this sort of shape, that semicircle, swung all the way around the z-axis, right? Which creates that sphere. What is my range for rho? 0 to 1, right? Remember, rho is the distance from the origin. If I take here the distance from this to any point on the surface of this, it's ranging from 0 distance from the origin to 1 unit from the origin. So all my limits are constants in terms of spherical coordinates. And so this integral, how would it look? I equals integral here, 0 to 2 pi, 0 to pi, 0 to 1, cosine of, this is all rho squared, which I raised to 3 over 2, so this just becomes rho cubed, times dv.
Rho squared.
How would I integrate that? Well, now it's just an easy substitution to do with this guy. Again, there's no thetas anywhere. There are no thetas on the inner integrals, so I'm going to throw out a 2 pi on the outside here. Integrating with respect to rho is just a substitution here. That's going to give me what? 1/2 sine rho cubed sine phi between rho is 0 to 1. Equals,
1/3.
so I plug in 1 for rho, I get sine of 1, so I get 2 pi sine 1. The half, this half kills that 2.
Shouldn't it be 1/3? 1/3?
Or 1/3? Yes. So that's 2 pi over 3 sine 1. And then if I plug in sine 0, it just kills it, so it's just sine 1 times sine phi up here. Integral of sine phi.
Oh,
cosine phi, 0 to pi, plug in pi, cosine of pi is? Cosine of pi? Cosine of pi is -1 times the negative, you get +1, minus, which this makes it a plus, cosine of 0 is also 1, so this becomes 4 pi over 3 sine 1. I don't.
Could you explain the drawing of it? That's the hardest.
The drawing?
Yeah, like I don't know how you I don't know the representation of these variables pretty much. Like I understand theta is with the xy plane.
Yeah, theta is just the guy. As always, if it's a full sphere, it'll go 0 to 2 pi.
Yeah.
So theta is running around in the xy plane. So that's your theta here, right? Now you sort of you want to talk about what part of the sphere is covered. Is it only the top half, the whole thing, the top quarter? Like you have to see what are the range of points, right? The sphere, you're hitting all points from here all the way down to the bottom, right? That travels from an angle of 0 measured at the positive z-axis all the way down to pi, right? You've covered an angle of 180 degrees by moving from here to here, right? So phi is just measured from the positive z-axis coming down, and it'll go all the way down until it hits the negative z-axis, right? So that's where we get the 0 to pi from.
And the rho starts.
The rho is just going from the origin and hitting the outside of the sphere, right?
Okay.
Now at any given time, the farthest the rho will go is 1, because the sphere is centered of radius 1, right? So we'll range all the way from 0 all the way out to 1, right? So that's how we set this up. You can get this guy, and the integral is actually not that bad. I'm not going to do it all the time, but let's just do it now. What would this look like in cylindrical, since we just finished that? That same integral, but now evaluated in cylindrical. What would it look like? Well, that part's easy.
R goes from 0 to 1.
R would go from 0 to 1. What would my Z go between?
Square root. Negative square root of
Negative square root.
1 minus R squared.
1 minus
R
R squared. The radical of 1 minus R squared. Right? And so what would this guy look like here? 0 to 2 pi, 0 to 1, minus radical 1 minus R squared, up to radical of 1 minus R squared. This would be cosine R squared plus Z squared, 3 over 2. R dz dr d theta. Can we integrate this with respect to Z? Impossible. We tried. Clearly impossible in rectangular coordinates. Turns out it's also impossible in cylindrical coordinates. And yeah, but spherical coordinates, it's actually, not only is it very possible, it's actually pretty easy. It wasn't even a big deal, really. It's simple substitution.
In the exam, are they going to tell you when to use cylindrical?
Usually not.
Figure out yourself.
One question that might come up, and I think I will put a problem like this on a test. Like, I'll give you a region, and I'll ask you to set it up in all 3 coordinate systems, or something similar to that, and I'd say evaluate one of them. There's about a 50% chance that something like that would come on your final. But other than that, they're not going to tell you what coordinate system to use. You just need to know which one's more convenient.
Just for like putting it in rectangular like interval, it would just be from -1 to 1, -1 for all 3, right?
Oh, no, because that would be a box.
Oh, okay, oh, yeah.
Right. If we're doing rectangular, I mean, it's impossible to do the integral, but the limits would look like minus 1 to 1, minus radical of 1 minus x squared up to radical of 1 minus x squared, minus 1 minus x squared minus y squared up to radical of 1 minus x squared minus y squared, cosine of x squared plus y squared plus z squared to the third over 2 dz dy dx. Right, but we couldn't even integrate this in the first place, so it wouldn't really matter. Let's do another example. Yeah.
I'm looking at basically, isn't like the formula for a circle or a sphere 4/3 pi r squared, pi r cubed? So why did we get that in?
What?
If the formula for a sphere is 4/3 pi r cubed.
The volume of a sphere.
Oh, okay. Yeah.
We weren't finding the volume.
Yeah.
Yeah, if I use spherical coordinates and integrate the function 1 dv, I would get 4/3
Yes,
pi rho cubed. Okay, here's a problem. Find the volume.
Draw it.
Sure. Okay, what does that look like? That sounds like a good idea. What does this look like?
Isn't that a sphere?
Yeah, I know. I said it was a sphere. It's the sphere. Blah. Okay. How does that look?
The z is negative z minus 1.
So that x squared plus y squared plus z minus 1 squared equals.
1.
Okay, so that's really the sphere. So how would that look?
It's just to
So the sphere is, the center is 0, 0, 1, right? So it's 1 on the z. And the radius is 1, right? So it's actually sitting right on top of the xy plane. Right? So my sphere is doing this. Right? Center is 0, 0, 1, goes up to 2, down to 0. And then I have this cone. So there's going to be a part going up here and a part going down here, but that part doesn't matter. We want it inside the sphere and the cone, which means it's going to be this guy. It's like another ice cream cone, except my sphere is now shifted up.
Just make sure you complete the square to find the.
Yes.
Okay.
Brought this over, completed this one. Right. So it's another ice cream cone. It's fundamentally different from the previous ice cream cone because the center is shifted, right? So set this up spherical. You'd think spherical because still there's a sphere here. It's a part of a sphere that we're integrating over, the object. So how would I set that up? Ideas.
And it's going to be 2 cosine. Yeah, it's only 2 cosine.
So theta from 0 to 2 pi. What else?
So T is going to be 0 to pi over 4.
T from 0 to pi over 2.
Phi is from 0 to what?
Pi over 2.
4. 4.
Pi over 4. Why is there confusion here? Why is it not pi over 2?
Because it's a cone.
Because it's a cone? Like, how do we know it's pi over 4?
Because of the diagonal.
Where's phi being measured? Where's, if we drew in the angle phi, where would it be? From the z-axis down, right? But we stop here. We stop on this line, right? That's protruding here. That's my angle phi. How do I know that's pi over 4? Tell me some ways we figure out that's pi over 4.
Because it looks just like x equals y.
Because it looks, I didn't draw it to scale. I just sketched out of my hand. It doesn't matter what it looks like.
You should look in either the xy plane, I'm sorry, the zx plane or the zy plane, and it'll be either z is equal to x or z equal to y, so that's 45 degrees.
Z equals to y. So you're saying look at,
You do the xy.
so you think of this as the xy plane? Right, so we're going to have like a side view,
Yeah.
and we have this guy coming up. Okay, and you said what?
And you know that. So
We
you-
know that this is phi.
Yeah. And basically, you could set either x is equal to 0 or y is equal to 0, and then you just have z is equal to x.
So I know this height here is z here. Then what?
And that's x squared plus y squared. Right there.
Where is that square plus y
The
squared?
width. What are you gonna call it?
The width here would be what?
Oh, radical x squared plus y.
Radical x squared plus y squared, which is?
It's r.
Right, but what is r here? Look at the equation. We're looking at z squared equals x squared plus y squared, right? So my z is actually equal to the radical of x squared plus y squared, right? Which is this length. This is actually also a z, right? So then I have a triangle where if I take the tangent of theta, tangent of phi, I get opposite over adjacent, z over z, which is 1, which means that phi equals pi over 4, right? There is another way. Again, going by this equation, right? My z is what in spherical?
Rho squared cosine, your rho squared cosine phi squared.
Rho squared cosine squared phi,
Yeah.
Right.
Yeah,
equals my x would be rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. How would I simplify this?
Cancel out all the rows.
Sure, I can cancel out all the rows.
Which is sine squared phi times r.
I can factor out a sine squared phi. What would I be left with?
Cosine squared plus, I mean, cosine squared theta plus sine squared
Cosine squared theta plus sine squared theta.
r. Can you say that?
That's not r.
That's one.
That's 1.
Oh,
So basically I end up with cosine squared phi is equal to sine squared phi. Right? Where's the cosine equals the sine? I know it's in the first, I'm thinking of this as the first quadrant, pi over 4 is where that will happen.
Was he necessarily wrong when he said that you would make the x or the y as 0, and they will make a 45-degree angle in the plane that you observed in?
If you made the x or the y equals 0,
Yeah.
Basically, it's looking at either ZX or ZY plane.
oh, if you look at the zx or zy plane and just look at that,
Yeah, exactly.
Is that
okay,
wrong?
that would make a forward, yeah, if we're looking at the trace of that ice cream cone in the one of the either the zx or the zy plane, yeah, you can think of it that way as well. There are tons of ways to do it. I just wanted to make sure you guys understand what's going into all this. Yeah, so you can think of it in this way, use SOHCAHTOA. You can think of it that way, just using your equations, just plugging them in and simplifying to something nicer. Yeah, you can think of projecting in one of these planes. Just figure out what it looks like when your theta is at pi over 2, right? We're in the ZY plane. It's going to be, if we're looking like in the ZY plane, it's just going to be that line where you know that this is pi over 4, because it's going to be the line z equals y and z equals minus 1. Right? So tons of ways to get this. Just want to make sure you know. So by the way, from now on, we just know for this cone, it's pi over 4, right? Phi equals pi over 4. Right? But I could have given you some other cone. I could have said that cone, and you need to know what's going on. Just like here, I didn't just give you a nice formula for a sphere. I didn't just throw a constant on the other side. I threw 2z on the other side. And you had to know how to change things, right? So I want you to know how you should be looking at things.
Wouldn't that cone just be b equals pi over 8?
Phi equals pi over 8.
Yeah, like if the cone, like when you said 4, I could give you that cone. You just add the 2 to the z. Just equal 2 times z equals.
Yeah, so I'd have a 2 here and a 2 here.
Yeah, so you just end up being pi over 8 divided by 2.
No, it wouldn't be the same. If that was a 2 there, what would that mean? That would mean that 2 is equal to tangent squared phi. Right? Which means that tangent phi is radical 2. Well, plus or minus. And then you just, phi is just the tan inverse of radical 2. So, yeah, so know how to look at this so that if I throw something weird at you, you know how to deal with it. Okay, so that's going to be my phi. How's my rho going to behave? 0 to 2 cosine phi. Where's rho measuring? From the origin to where? It can extend as far as here. It's extending to what surface at any given time? It's extending to that sphere. Okay, so what's the distance from the origin to the top of this sphere? Clearly it starts at 0, but going up to what? The distance from here to here is not 2.
But
Yeah, but that doesn't matter.
Remember, our sphere is not centered at the origin.
2 times.
So it's not 2 from everywhere, right? For example, if I say go from 0 to here, is that 2? That's not 2. So it's not going to be constant anymore because we're not centered at the origin. Yeah, we know that x squared plus y squared plus z squared equals 2z, which means this means that rho squared is equal to 2 rho cosine phi, which means I can say rho is 2 cosine phi. Right? So my rho goes from 0 up to 2 cosine phi. So those are my limits. So now how do I find the volume? Triple integral of 1 over, I didn't call this anything, 1 dv, set it up. So d rho d phi d theta, theta's on the outside, 0 to 2 pi, phi is on the inside, 0 to the power of 4, rho is on the inside, 0 to 2 cosine phi of 1, rho squared sine phi d rho d phi d theta. And what's that? Well, I'm doing d rho first, so I have to integrate this, right? I could take out that 2 pi because there's no theta on any of the limits and there's no theta in here. So there's going to be a 2 pi on the outside. Going to integrate rho, I'm going to get what? 1/3 rho cubed. So if I plug this guy in here, I get 2 cubed, which is 8 times 2. It's going to give me a 16. Then it's going to give me cosine cubed phi sine phi. Plug in a 0, everything dies, so I just have this. So what's the integral of this?
Cosine of the 4th over 4.
That's the integral. Cosine to
Oh,
the
negative.
fourth.
Sorry, negative.
Negative. Minus 16 pi over 3 cosine to the 4th phi over 4. Between 0 and pi over 4. So 4 cancels into this 4 times. So I get minus 4 pi over 3 times cosine of pi over 4.
No, radical 2 over 2.
Radical 2 over 2. If I raise that to the 4th power, what do I get?
1 over 8.
2.
What?
1 over 8.
I get 1 over radical 2 to the 4th power minus cosine 0 is just 1. Alright, so this is 4 pi over 3 times 1 minus, this is over 8?
Oh no, sorry, 4.
It's over 4. So this is 4 pi over 3 times 3/4. So it's just pi.
Wait, I'm sorry, I missed what happened to this time.
Substitution, u equals cosine.
Oh, what happened to minus 4?
I swapped the insides. So at this minus 1, I changed to 1 minus pi. So I took that sign out. Time's up. That's basically the idea. I had a couple more examples. We'll continue next time. So next time we'll finish up on spherical. You can start the homework just to see how to set some stuff up. We'll go over some more examples. The homework for cylindrical I'll take next time. And we will start sequences and series. I am not, what?
Exam is after December 1st.
Today I was flipping materials.
Wait, when did I say the exam?
After Thanksgiving. After
I said after Thanksgiving?
A week from today.
A week from today, like the 24th. No?
So it was gonna be the first.
So, I don't care. Like, you want it after Thanksgiving or before?
Do you want to grade exams over Thanksgiving break?
Yeah.